Hi friends, let's start with a chapter called Periodic Table. It has the roots of the 9th standard which need to be powerful. Then only I expect you all to come to this 10th and have the audacity to study with me. So first go back to the 9th standard, make your base strong and then come to the 10th standard, right? However, I know my students very well. So I don't expect anything from them much. So I am definitely going to give you a brief about the 9th as well. Then only that connectivity will be formed for the 10th standard and that foundation, that base will be built. In 9th standard, it all started from 3 people. Mendeleev, Dobrenier and Newland. They were the ones who started with the positioning, the locationing of the elements in a particular format. Not in a table though, but in a particular format. So if I happen to talk about this chapter, periodic table, alright, just skipped out guys. The weightage of the chapter from the board's perspective is approximately 7 marks. Yep. And as I said, how did this periodic table come into existence? Yep. It all was started with first Dobrenier, second Newland, and third Mendeleev. Come into existence. Okay, so first Dobrenier. Second, I'm Newland. Hi students, I'm Newland. I am going to arrange the elements again in the increasing order of atomic weight, atomic mass. The speciality of my table is the elements are arranged in increasing order of atomic weight. Yes, and every eighth element shows similar chemical properties to the first element. Then came Mendeleev. Hi guys, I'm Mendeleev. What I did was, I also arranged the elements in the increasing order of atomic weight. But I gave a table. In the table, there are rows horizontal called periods. There are vertical groups called columns. Yeah. And I am arranging the elements in a tabular format. So these were the 3 people who failed miserably. The same mistake all 3 of them made, and it was this. All of them arranged the elements in the increasing order of atomic weight, atomic mass. That was a problem. Then came the person called Moseley. Moseley saw the failures, the drawbacks, the limitations of all 3 of them. He changed the concept. He said, fine, the table looks nice, it sounds good. Let's now arrange the elements in the increasing order of atomic number. That is Z. Atomic weight is represented by capital A. Because we know atomic weight is the number of protons plus neutrons, and atomic number is nothing but just protons or electrons. So Moseley changed the dimensions of placement, and then this was a bit more, polished and restructured into a periodic table. So Moseley's periodic table was actually the successful one. And in Moseley's periodic table, let's study the salient features. So the salient features of the modern periodic table, or a derived form of Moseley's periodic table, is as follows. First, the elements were arranged in the increasing order of their atomic weight. So increasing order, I'm just writing the briefers. Atomic weight? No, atomic number. What weight? Atomic weight was a flop show by them. Come on. You're sleeping or what? Come on. Yes, atomic number, not mass number. The second pointer, there were 7 rows. Rows are always horizontal, students. and they were called periods. And there were 18 columns. They are vertical and they were called groups. So this was how a structure of a table was. Alright, now remember, since the elements are arranged according to their number of atomic number, that's the number of electrons, we are talking about the electronic configuration. So I can say the table was based, or it was dependent, okay, the location, the position of elements was dependent on the number of electrons. That is electronic configuration. There were many nice properties the table showed. It showed, just giving you a reference, these horizontal are periods and these are vertical columns. So these are columns and these are rows, periods. Now remember, the speciality of the placement was down the subgroup in a column, the elements which were placed, which were positioned, they show similarity in the chemical behavior. Chemical behavior, that means when they react, their behavior almost remains very much similar to each other. For example, you take a metal, you react it with a dilute acid. Of course, what is formed? A salt and hydrogen. So can I say that you take any damn metal, you react it with a dilute acid, majority of the time, the characteristic feature remains the same. You are going to get a salt, of course a different salt, and hydrogen gas. So can I say down the group, the chemical behavior, the chemical properties of the elements were similar. Across the period, this way, horizontally, left to right, the elements were differing by chemical nature, yes, for sure, but they had the same number of shells. Now what's that? That's the significance. So if I happen to talk about first the significance of a period means row, horizontal. What's the significance of the period? Elements in the same period, elements which are in the same period, they have same number of shells. That is, the number of shells remain the same. So if you have an example, take an example, sodium, magnesium, aluminium, it goes on up till argon. Okay, can I say the configuration of sodium is 281? It has 3 shells. Magnesium 282, argon 288. Can I say in this row, horizontal period, each of the element has how many shells? 3 shells. That's the significance of a period. Alright, if you talk about the significance of a group, that is column. First, the valence shell configuration remains the same. Now what do you mean by that? I'm not understanding. I'm sorry. Nice one this is. Check this, guys. I can say in the first group, you have hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. There you go for it. Francium is a radioactive element. I'm going to discuss about this after some time. Just taking an example to explain this concept. Configuration, valence shell configuration. Check. 1 electron in the last shell. 1 electron in the last shell. 1 electron in the last shell. Now that's monotony. Can I say in the example I've taken, down the group, check it, down the group. Can I say the last shell, each of the element has one electron and it is equal to the column number. This is column number 1, Roman number 1a, group number 1. That means the elements which belong to the first group, I'm going to draw the table in a moment, hold please. Okay, the elements which belong to the first group have one electron in the outermost shell. That means that is called valence shell. The configuration remains the same. Down the group, they show similarity in the chemical properties. So similar chemical properties. This was the significance, the importance, the importance of a group. So this was just a base, a brief for the 9th standard, right? From the 9th standard perspective. 10th standard, we're going to talk about a bit more in depth about the periodic table. However, if I talk about the salient features, right, it was the table, okay, the table which was made, the periodic table, there were few properties which were studied. And those properties were like atomic radius, ionization potential, electron affinity, electronegativity, yes, metallic and non-metallic nature. So based on the positioning of the elements, based on the location of the elements, we are going to study about all these 5 periodic properties. What do you mean by periodic? When I'm talking about the word periodic, it means after regular intervals of time. That means, can I say, as we go ahead and then we come down, can I say after regular intervals of time, there is some sort of a similarity in properties. And those periodic properties, we're going to study, we're going to have a glance, and we're going to by heart it in a while. Talking about the actual periodic table. Let's begin, guys. Check. I'm not going into super depth, but yes, much of a depth. Okay, so now the periodic table looks something like this. I'm going to go a bit fast with it. Yeah, that's what it looks like. Buildings, a set of buildings. This is called group 1, group 2, group 13, 14, 15, 16, 17 and 18. Start learning with me. Again, a portion, it's of 9th standard, right? But you should know it. We also call it as Roman 1A, Roman 2A, Roman 3A, 4A, 5A, 6A, 7A, and 0. Group 0, we come to it. Out here, we have the groups from 3 to 12 or Roman number 1B, B to 7B and 8. That's how it goes. Yeah. Now, first thing, these group A elements, okay, having a quick review, group A elements are called normal elements. So if I talk about group A elements, we call them as normal elements. And group B elements, we call them as transition elements. Now, what is the difference between them? Normal elements consist of metals, non-metalloids and non-metals. However, the transition elements out here, they consist of weak metals, only metals a bit weak in nature. Okay, first. Second point, normal elements, this and all of these, yeah, the normal elements, only the last shell, okay, the last valence shell is incompletely filled. However, for all these transition elements out here, the last and the second last, that is the valence shell and the penultimate shells are incompletely filled. So these are 2 points of differentiation between normal and transition elements. If I fill the table, guys, yeah, let's say this is going to be your period 1. So period 1, period 2, right? Then we have period 3, period 1, period 2, period 3. We have then period 4, period 5, period 6, and finally period 7. In period 1, you have hydrogen. Hydrogen can also be a part of halogen, 9th standard hydrogen chapter. And we have helium, inert, duplet, stable. Then we have lithium, we have beryllium, we have boron, carbon. Okay, after carbon, we have nitrogen, oxygen, fluorine, and neon. After neon, we have sodium. Okay, after sodium, come on, magnesium, you know it. Aluminium, silicon, phosphorus, sulfur, chlorine, argon. After argon, we have potassium, K, calcium. Potassium, this is K, and calcium. Right. Calcium is the 20th element. So I can say this is the 20th element, and all I need from you all to know is the 20th, up till 20th element. Also, I want you all to know a few more apart from this. We have hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, where francium is radioactive in nature. Out here in the 17th group, I want you to remember a few more. Fluorine, chlorine, bromine, iodine, astatine, and no need to remember this one. Helium, neon, argon. So we have krypton, xenon, radon, and you don't need to remember this. So this was about the normal elements and the transition elements which I have written, right? And we have seen the differentiation between both of them. Alright, so these are the elements which I have written on the board, should be by-hearted. Alright, after this, guys, we're going to study about the number of elements. In the first period, we have only 2 elements. Hence, we call it as the shortest of the period. We have 8 elements in the second period, 8 in the third period, 18 in the fourth period, 18 in the fifth. Period 6 has 32 elements and period 7 has 26 elements. Now, this is a thoda slightly, an antiquated sort of a periodic table. However, even period 7 now has much more elements as what I have written. Alright, so if I talk about the shortest and the size, I've spoken about the numbers. Period 2 and period 3 together, they have the same number of elements. They are said to be short periods. Period 4 and period 5 are stated to be long period. Even period 7 is a long period. And period 6 is the longest of the period. So guys, which is the longest period? It is period 6, consisting of 32 elements. And period 1 is the shortest of the period, consisting of 2 elements. Now, usually kids tell me, sir, there are 18 columns. So obviously, in period 4, there are 18 elements. Period 5, there are 18 elements. Alright. Period 6, sir, are also 18 elements, right? Then how did you write 32? How is it possible? I tell them, nice question. Listen, at the bottom of the series, we have a continuation of period 6 and period 7. So we have period 6, we have period 7, consisting of 14 elements each. So out here, guys, in this period, this one, there are 18 elements out here, 18 of them. 18 plus 14 makes it 32. That's how you have 32. In the 7th period, out here, you have 12 elements. 12 and 14 out here makes it 26 elements. That's how we get 32 and 26 as the number. And these two periods or these two rows which are placed separately at the bottom of the periodic table are called inner transition elements. And there is a special name given to it. So can I say the inner transition elements are the two periods, 6 and 7, a continuation. And they consist of lanthanides, which are also called rare earths. And we call the period 7 as actinide, also called it as radioactive elements. Alright, starting from cerium to lutetium or lutetium, my wish, cerium to lutetium, and thorium to lawrencium. This is the start and the end. No one's going to ask you, but just remember it, right? So this was about the inner transition elements, which are also called the radioactive elements, right guys? So all of you all, till now, this was a briefing about the periodic table. Now, if I talk about the first group, down the group, I know that the valence shell configuration remains the same. And we have studied about the significance of a column, of a group, right, with this. Now, always remember one thing, students. If I talk about the first group, the first one, we call it as alkali metals. So group number 1 are called alkali metals. Group number 2 is said to be alkaline earth metals. These are transition elements. From 13 up till 16, we call them as post-transition elements. 17th group is said to be halogens, and 18th is said to be inert, the zero group. So always remember, students, if I happen to ask you a differentiation between any of these, I'm going to give you a quick pointers. First one, come on, alkali metals. Let's consider sodium as an example. Can I say sodium is a very active metal? Point number 1. Second, the valency is 1 plus to be more precise, because sodium gives away one electron. It gives away an electron. It becomes electropositive. It is a reducing agent because it gives a negative power to someone else. So it undergoes oxidation, rise up, right? And so I can talk about the valency, the electropositivity. Then we can talk about a very active metal, reducing agent, undergoes oxidation. Okay, so these are all the properties of alkali metals and also alkaline earth metals. The same properties, because they both are metals. If I talk about halogens, the 17th group, they are electronegative because they take away the electron, right? They take away an electron and they become negative. They get reduced. They are oxidizing agents. And the valency is 1 minus. You can say that is the oxidation number, 1 minus for the halogens. Inert gases, on the contrary, inert gases, right? They have zero valency. Why zero valency? Because they are stable. They don't want to take, share or give or there is no transfer of electrons because they are already stable, right? They have octet or duplet. So they have zero valency. They are not reactive under normal conditions of temperature and pressure. Transition I have already spoken about. Normal I have already spoken about. The post-transition elements, these ones, group 13 to 16, consist of metals, metalloids and non-metals. They consist of everything, every damn thing. The first two consist of metals only. 17th consists of non-metals. So this was all about the generalized concept of non-standard periodic table. Now talking about the periodic properties and the bridge elements, two new things. So first, if I talk about the bridge elements, I give you an example to explain this concept. We usually talk about period number 2 and period number 3 in order to explain this concept. Listen, in period 2, I have lithium starting, lithium. We have beryllium, we have boron, we have carbon, we have nitrogen. This one. Lithium, beryllium, boron, carbon, nitrogen, oxygen, and so on. Just underneath lithium, we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and so on. Always remember, the bridge elements are those elements which have a diagonal relationship I'll tell you what do you mean by a diagonal relationship. Now, can you see these are all diagonals which I've made? You know what? In a geometry, right, isn't this said to be one of the diagonals? Of course, yes. So what's a diagonal relationship, guys? Remember, if you talk about period 2 and period 3, these elements which are diagonally placed, they show similarity in the chemical properties. Now, we very well know that if you go down the subgroup, the chemical properties are similar. That is for sure. It goes without saying. But there are few elements in period 2 and period 3 which show even a similarity in the chemical nature. Hey, lithium, it is like magnesium. Hey, this beryllium is something like aluminium. Matlab, the properties are very much similar of magnesium with lithium, aluminium with beryllium. All right. So even there is a diagonal relationship. So if I happen to write in short in the exam, first I need to draw this and show this representation, and I can say that there is a diagonal relationship. Diagonal relation means what? It means that there is similarity in chemical properties. Diagonally, please. All right, so this was about the bridge elements. Now, if I talk about the periodicity in properties, we are going to first study about atomic radius. Then we'll be studying about the second property is ionization potential. We'll be studying about electron affinity, electronegativity. And finally, we'll study about the metallic and the non-metallic nature. So now let's study and start with atomic radius as the first periodic property, right? So till now what we have done is the main chapter starts from here. The periodic properties. This was all just a briefing of 9th standard, a quick review of 9th I've done with you. You should know the basics, right? Now remember, while speaking about all these 5 periodic properties, I am going to take an example of the second period, or let's take example of the third period, this one, and the first column. So I am repeating what I spoke in order to understand, okay, to just, analyze the periodic properties. I am going to take an example of the third period and the first group. And whatever I'm going to speak, that pattern, right, that theme remains the same for all periods and for all groups. Always remember, right? So just go through this, all right? Please, 9th standard, as I said, you need to know it. We jump to the 10th, the atomic radius. Let's start with atomic radius, the first periodic property. I'm just writing short AR, atomic radius. Atomic radius, just check. I'm drawing a diagram. This is a nucleus. Henceforth, I will call it as mother nucleus. Mom loves students. Mom loves kids. Mom loves their children. So this is mother nucleus having neutron, proton. Let's say this is the innermost shell, the K shell, the second shell. I'm just making 2 shells. Okay, if I define what's atomic radius, it is the distance from the center of the nucleus to the outermost shell. So can I say atomic radius is the distance from the center of the nucleus to the outermost shell, outermost orbit. That's what atomic radius is. Remember that, first thing. Okay. It is measured in unit called angstrom unit. We call it as A0. This is the unit of measurement of atomic radius. Now let's study about the trend, the pattern. As we go from left to right in a periodic table, what happens to atomic radius? Does it decrease, remain the same, or increase? So henceforth, please repeat with me. I'm going to speak in this way. As we go across the periodic table from left to right, how is the nature? Similarly, Down the group, as we go down in a periodic table from top to bottom, what will be the nature, right? What will be the character of the atomic radius? How will it be affected? That's what we are going to study now. All right, let's start. So now please remember one thing, the terms which I'm going to use. Nucleus is mother, mom. If I talk about electrons, these are children, these are kids. Okay, we are going to study in that reference. Okay. There is something also called as nuclear charge. Before I jump to the concept, let's see what is nuclear charge. Let's understand this terminology. Nuclear means coming from the nucleus. Charge means, can I say something like positive, negative? Yes, charges. You know what charges are. So nuclear charge is nothing but a force of attraction. A force of attraction, a bonding, a linkage, electrostatic force between the nucleus and the electron. It is a pulling effect. Okay, so if I say there is more number of neutron protons, obviously if there are more protons, there are more electrons. So protons increase, electrons also increase, because don't we know that an atom is stable? It is electrically stable. That means in an atom, the number of protons and the number of electrons are the same, right? So if there is a rise in the number of protons, there will be an equivalent rise in the number of electrons. You know that, right? We say the nuclear charge increases. Nuclear charge means the pulling effect, the force of attraction between the protons and electrons. There are more in number, more in magnitude, it increases. So keep it very simple. If protons increase, then obviously the electrons will also increase. And I can say the nuclear charge increases. Remember, this is like a base. Everything increases. A direct proportionality, people. Right? So let's study about the nature of atomic radius across the period and down the group. I told you I'm going to take an example of the third period. So in the third period, we start our game. We have sodium, magnesium, aluminium, goes on. Second last element is chlorine, and then we have argon. So if I talk about the electronic configuration, listen to me very, very, very carefully. Check. We start. Across the period from left to right in a periodic table, can I say the number of shells remain the same? Just made a small error, 288. Yeah. The number of shells remain the same. This sodium has 3 shells, 3 shells, 3 shells, 3 shells. So ideally, can I say, like a layman, that if the number of shells are the same, the atomic radius should be the same, right? But sorry, no, it is not the same. Look what happens. As we go from left to right, can I say, ideally, atomic radius should be same, ideally, but it is not the case. First pointer. Second pointer. I say that the number of protons and the number of electrons increase. Come on, yaar, it's increasing. Can't I see? 1, 2, 3, 4, 5, 6, 7, 8. The number of electrons are increasing. So the number of protons are also increasing. So can I say the nuclear charge also increases? Oh, come on. Nuclear charge has increased. Nuclear charge increases. If nuclear charge increases, the pulling effect, the attraction, closeness increases. Protons, more protons will say, hey electrons, come to me. Look, there are more children. The number of children, kids in the outermost shell are increasing. The mother nucleus calls the child. Hey, come son, kids all come, please come, eat food, go. Mom loves the kids, yeah, mom loves their kids. So can I say that always remember, the nuclear charge increases, the pulling effect increases. So nuclear charge increase, force of attraction increase. And therefore the atomic radius decreases. So guys, look at my gesture. Sodium. magnesium, aluminium, chlorine, argon. Oh shit. What I did? Look at this. Big, small, 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 big. In general, yeah, that's an exception. Wait now. I know you're inquisitive about what's going on. But can I say in general, as we go from left to right in a periodic table, the atomic radius decreases because the force of attraction increases. The pulling effect increases. And obviously when the pulling effect increases, come on, they love each other. They come close to each other. A bond is developed. They become small. All right. Now, that exception. Out here, when I went, I suddenly increased the size. Check. That's an exception. Argon, okay, argon, this is the basic. Atomic radius decreases. This is my answer. But what I'm writing is an exception. Okay, argon is big in size. Reason? What is the reason? Reason number one, argon is electrically stable. Can I say argon is inert? It has 288 electrons and it has octet stability. Octet stability. Therefore, the electron repulsion is more. Now listen to me. In argon, the mother nucleus, okay, the mother nucleus, there are 8 children in the outermost shell. Mother nucleus tells, hey kids, come to me, alright, we'll eat together. Now these kids are useless, hopeless kids. What these kids do, they fight amongst themselves. It's stable, they have a lot of money, they have that egoism, that power, that useless power of money. Shit, I don't like that. But these 8 kids, they fight. We won't eat with him. This kid says, I'm not going to eat with him. He says, oh, come on, get lost. I will eat in my own room. So guys, can I put it this way? These electrons, which are negative, they will have an electron repulsion. So despite mom calling them together, that come attraction, no, these electrons, these kids, they don't listen to the mom. And because of this electron repulsion, they try to move away from each other. So when they move away, atomic radius increases. So 2 reasons. Reason number 1, stability of argon, and reason number 2 is the electron repulsion. So always remember, because of these 2 reasons, the problem is the last one has slightly more atomic radius as compared to the others, right? All right, let's go down the group. So down the group, I talk about the first group and I explain. The trend remains the same for every period and for each group, please. Okay, atomic radius down the group. Group number 1, we have hydrogen, lithium, sodium, we have potassium, rubidium, cesium, francium. Now students, francium is radioactive. This is radioactive. So usually most of the teachers, they don't consider francium into the competition. It's cheating, it's cheating, yaar. These all people are normal and this is strong. So that's not fair deal. So people, we stop at cesium and we will discuss up till cesium only. Okay, down the group, what happens? Check. This is more beautiful. Hydrogen has 1 shell, one orbit. Lithium has 2 orbits. Sodium, 1, 2, 3. As on cesium, it is in the 6th period. Hey, come on. Hydrogen is in the 1st period, so it has 1st shell. Lithium in the 2nd period, it has 2 shells. Sodium in the 3rd period, it has 3 shells. Cesium is in the 6th period. So it will have 6 shells. 1, 2, 3, 4, 5, 6 shells. Oh, come on. Look at this. As we go down the group, can I say the size is obviously increasing? It's very common sense. But look at my explanation. I will confuse you all. Check. Answer to my questions. Come on. Down the group, number of protons are increasing. Of course they are. Of course, man. This has 1 proton. The configuration is 2 1, 2 8 1. This is 2 8 something 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 1. Right with this. Check this. As we go down, the number of protons and electrons are increasing. So if the number of protons, electrons increase, the nuclear charge also increases. Yeah, we've seen that. So I will say protons increase, electrons increase, nuclear charge increases. Perfect. So if nuclear charge increases, the pulling effect also increases. Hey, come close children, let's have a bond together. So because of the pulling charge, ideally the radius should decrease, atomic radius should decrease because of the nuclear charge increase. Are you understanding what I'm saying? Think, it's interesting. Don't sleep. Okay. So atomic radius also decreases. Atomic radius should decrease. But remember one thing, the number of shells are increasing. Oh God, there was 1 shell, 2 shells, 3 shells. So there is a rise in the number of shells. So I can say that this is not good here. Listen, the second point is number of shells are increasing. So now this is a contradictory effect. One of the factor is trying to decrease the size. Other factor is trying to increase the size. Listen, number of shells are increasing. If the number of shells increase and because of this, radius increases. But the number of protons, electrons and charge is increasing, so force of attraction is increasing, thus the radius is decreasing. That means this factor tries to increase the atomic radius, this factor tries to decrease the atomic radius. So look at my gesture. Let's see who wins the competition. It is a contradictory effect. Check my gestures properly. This was hydrogen. Look at my hand, the size. This was hydrogen. Lithium, 1 shell increases, but pulling effect increases, so it will shrink. Sodium, 1 shell increases, but pulling effect increases, slight shrink. So tell me, though there was a shrinking effect, there was a pulling effect, but wasn't the pull small? So basically, the pull could not win. The pull could not defeat, dominate, overcome the number of shells, the effect because of number of shells. So I can say this, because of the rise in the number of shells, there is a vast increase in the size. And because of the nuclear charge, there is a small decrease in the size. So basically, if I go down, okay, and average it out, the resultant is that the size increases. So I can say number of shells win the game. The number of shells dominate over the nuclear charge, and therefore the atomic radius increases. So now guys, if I happen to summarize it out, okay, remember a summary to be written out here. Across the period, atomic radius decreases, and down the group, atomic radius increases. This is the summary. And if you ask me, sir, in the entire periodic table, who is the smallest element? And the smallest element having the smallest radius is helium. And who is the largest element? The largest of all elements having the largest atomic size, ideally it is francium, but you can say it is cesium. So now this is a contradiction. It can either be francium or cesium. I am repeating. The element having the maximum size, okay, maximum atomic radius is actually francium. But as I said, francium is radioactive in nature. So we can consider it out to be cesium, right with this. So this was all about the first periodic property, which is atomic radius. Go through it and we shall compete with the next one, ionization potential. The next concept, the next periodic property, ionization potential. All right, ionization potential, all right, what exactly it is? Check. First, I'm speaking the definition. It is the amount of energy required to remove an electron from the outermost shell of an isolated gaseous atom. Wait, it is the amount of energy required to remove an electron from the outermost shell of an isolated gaseous atom. Let's understand this. If I'm talking about a mother nucleus, neutron, proton, and if I'm talking about, let's make 3 shells and understand the concept, right? I'm just making the electron in the last shell, the final shell, the valence shell. Now this is the electron. Let's pick up a story. This is mom and this is son. Mom loves the son very much. Hey son, come and eat food. Mom talks to the son. Son is not very much interested. He doesn't give a damn about the mom. Not a good son, not a good son. Now listen, mom has cooked chapati, mom has cooked vegetables, rice, okay, the nourishment, the nutritious food for the son. Son is not interested in eating the food. Now, a stranger comes from outside. He's a bad man. He comes. Right? So something like this. He gives chocolate to the son. He tells the son, the bad man speaks, haha, hey son, come here. Come to me, I'll give you chocolates. Come to me. Now, can I say these chocolate, the chocolate is the energy. That is the energy. Okay, required to do what? To remove the sun, to remove the electron from the outermost shell of one isolated atom. We're only going to talk about a single atom as of now, not multiple atoms. So can I say it is the energy? Energy out here is the chocolate. Given by whom? Given by the bad man or given by us. Okay, to remove the electron, to remove the sun from the bond of the mother, from the outermost shell. That's ionization potential. So I can say, if I talk about the behavior from left to right in a periodic table, so can I start with across the period? Taking an example of the third period again, third period only. Now that's monotony. I like that. We have sodium, magnesium. It goes on chlorine and argon. So this is 281. This is 282. It goes on up till 287 and 288. Now check this, all of you. Tell me, I need to remove just 1 electron from this, 2 electrons from this, and 8 electrons from the last one. So can you tell me one thing which is easy? To remove 1 electron, that means I have to drive one child out here. I just need to give him some sort of a bribe. I just need to tell, hey son, well, there is only one child, 1 electron, 1 kid. Yes, I just need to bribe him. Isn't this easy? It's very easy. So I have to supply less energy to remove 1 electron. In contrast to this, out here, argon, I need to supply so much energy in order to remove 8 electrons. So in which case the ionization potential, the energy required be more, can I say argon. So as I said, across the period from left to right, number of protons and number of electrons increase. Therefore, the nuclear charge, in board exam you can't write NC, but out here remember NC stands for nuclear charge. Okay, the nuclear charge increases. If nuclear charge increases, energy required to remove the final electron, the electron in the valence shell also increases. Therefore, amount of energy increases, and I can say that the ionization potential also increases. So across the period from left to right, we need more energy, we need to supply more energy in order to remove the final electron, the electron in the valence shell. Thus IP increases. Okay, let's study down the group. Down the group, again, hydrogen, lithium, sodium, potassium, rubidium, cesium. Francium I'm not talking about, please, come on. This is 1, this is 2, 1, this is 281, it goes on. Now, answer to my simple question. In all of them, if I draw a simple shell, neutron, proton, hydrogen, 1 electron in the outermost shell, cesium, 6 shells, 1, 2, 3, 4, 5 and 6. Alright, 1 electron in the outermost shell. If you check the comparison between both of them, answer to my simple question. Isn't the atomic radius very small in case of hydrogen? So the atomic radius is less. Out here, the atomic radius, the distance between the mother and the sun is so huge, so far. There is no force of attraction. There is no strong bonding. The mother is not able to control this child because it is so far from the child. So can I say this child is far? It's not getting love of mother. This child is under the influence of mother's love. So can I say the bond, the love between mom and child is awesome out here, awesome. No love, no care, concern. So can I say the chances of this child getting swayed by energy, by the chocolate is very easy. Okay? If you supply a chocolate to this child, can I say this child will easily be lured by the chocolate, yeah? So isn't it very easy to remove this electron from the outermost shell? It is difficult to remove this electron because if I talk in technical language, atomic radius is less. There is a good force of attraction. Out here, the force of attraction, electrostatic force of attraction is less. And if the force of attraction is less, ionization potential is also less. You can easily remove this electron by supplying less energy. And out here, you need to supply more energy. To remove the electron in the outermost shell. So basically, if I happen to summarize it, guys, ionization potential down the group decreases. You need less energy as we go down. So if again a summary as I said, okay, in a tabular form, across the period, down the group. Can I say across the period the ionization potential increases and down the group ionization potential decreases. Now if you'll ask me that which element has the maximum IP and which has the minimum IP, I will say, guys, the minimum ionization potential, the element is cesium. So I can say the least ionization potential is with cesium. Reason, check. Cesium, the child is very far from the mother. So you can supply less chocolate. Less chocolate means you can even give him an eclair. Okay, a simple eclair, and still the child is gonna leave the shell, leave the orbit and go with that stranger for that chocolate, for that energy. So can I say the energy supplied is very less. The greed is less. So I can say it's very easy to remove this electron from the outermost shell of cesium because the force of attraction is less between the nucleus and the outermost electron and the electron in the outermost shell. And the maximum ionization potential, the element is helium. Helium, first of all, it is stable, duplet. It has 2 electrons in the outermost shell, and those 2 electrons first are stable also. They have a lot of money. I don't give a damn about chocolate. Yeah, come on, I can buy an entire chocolate house by myself. That's what helium electrons say. And the second thing is they are close to the nucleus. If they are close to the nucleus, the force of attraction is tremendous. So helium, you need maximum energy in order to remove the electrons from the helium atom and minimum energy to remove the electrons from the cesium atom. So this was the concept of ionization potential, the bad man concept. Yeah, hope you've understood. Any doubt? You can just let me know for sure. The third periodic property, electron affinity. We call it as EA. Alright, electron affinity, it is the amount of energy released when an electron comes into the outermost shell of an atom and it becomes an anion, to become an anion, to make it an anion. Now, this is exactly a contrast to ionization potential. Listen now. There is again that mother nucleus, nucleus, and the outermost shell. You remember the sun had left the orbit in ionization potential. The bad man came, he offered chocolate to the sun, and he took the sun away with him. Now the sun realizes, shit, I miss my mom. I want my mom. I want to go back to my mom. So mom puts a condition. Listen, son. If you want to enter back into the orbit, the electron needs to enter back into the orbit. Can I say the energy has to be released? So now an electron comes and enters into the orbit. He needs to give away, leave that greediness. Leave away that X greediness, the factor, which he had taken. So I will say it loses. There is a loss of energy. There is a loss of chocolate. And finally, the electron can enter into the outermost shell. So you can correlate it that way. So it is the amount of energy which is released for an electron to enter into the outermost shell of an atom. And when an atom accepts an electron, obviously it becomes negative in charge. We call it as an anion. Cations are positively charged ions, anions are negatively charged ions. So this is what electron affinity is. Simple language, the need, the thirst, the want of electrons. Simple. Alright. The pulling effect of electrons. That's electron affinity. If you talk about the property, the nature across the period, behavior across the period, let's see it. So across the period from left to right, we're going to always speak about the third period. So we have again sodium, magnesium, aluminium and so on, chlorine, and we have argon. 288, 287, 281. Now answer to my simple question. There is an electron out here. Electron is flowing. An electron is coming in its path. Where will electron prefer to go? Who will pull the electron stronger? Can I say chlorine will pull this electron more strongly? Reason is it needs one electron to become stable. Sodium needs 7 electrons to become stable. So obviously the pulling effect, the power of chlorine in this row, in this series which I have written, is the maximum. So can I say the pulling power of electron, the affinity, the liking of electron is more shown by chlorine in this period. So I can say as we go from left to right, the electron affinity increases because the nuclear charge has increased. The pulling effect of electron increases. So I can say across the period from left to right, yes, across the period from left to right, nuclear charge increases, the pulling effect of electrons increases, and I can say therefore electron affinity increases from left to right. Okay, let's talk about down the group. One more thing, argon has zero electron affinity because it doesn't want, it is already stable. Electron can never go to argon. So I can say the inert gases have zero electron affinity. They have zero electron affinity. Fine. Talking about down the group. Down the group. Alright, first, again, hydrogen, lithium, sodium, potassium, rubidium, cesium. Okay. Fine. Now one electron is coming. Now I very well know that one electron will be accepted by none of them. Because obviously now, if they accept one electron, it will do no good. Because even if one electron enters into lithium or cesium, can I clearly say they are still not going to be stable. So ideally, I should explain it using the halogens. That's more precise. So let me take the 17th group to explain my concept more vigorously. So I'm talking about halogens now. So we have halogens starting from hydrogen, may be a part of that group, not always. We start from fluorine, chlorine, bromine, iodine, astatine, and so on. Tell me one thing, 27, 287, it goes on. Tell me one thing, who is closer to the mother nucleus? Obviously fluorine, it has only 2 shells. Chlorine has 3 shells, 1, 2 and 3. So tell me one thing, the atomic radius of fluorine is small, the atomic radius of chlorine is big. The force of attraction in fluorine between the mother and the sun is hard, is strong because of the small atomic radius. So tell me which will have a more pulling effect. I think it has to be fluorine. Fluorine will easily pull an electron, okay, to become stable because of the high electron affinity, the liking and the closeness, because the atomic radius is less. And as we go down, the pulling effect, the pulling power decreases because the electron, the shell starts getting far. Far means the force of attraction decreases. So I can say down the group, electron affinity decreases. So electron affinity decreases down the group. So if I happen to now analyze, summarize, it goes this way. Across the period, the electron affinity increases and down the group, the electron affinity decreases. Yeah, that is the whole ideology. So we have seen that if in one of the context, if it increases, the other context it has to decrease. So if across the period something decreases, down the group it has to increase and vice versa. It's always going to be different behavior, inverse proportionality. Remember, across the period and down the group, everywhere. Okay, so if you ask me, sir, which element has the maximum electron affinity and which element has the minimum electron affinity? So I can say the minimum pulling power is of cesium. Cesium, first of all, this one electron is far from the mother nucleus. In cesium, there's only one electron in the outermost shell. And that poor kid is so far from the mother. Mother cannot control that poor kid. How is it going to control one more kid who is going to enter the orbit? Please understand. In the cesium, if I make the outermost shell, this is the 6th orbit. The mother has no much of attraction, no control over her single sun, over the single sun. If she can't control this sun, how on earth, how the hell is she going to control a new sun who is going to enter the orbit? Yeah, so it's not possible. So cesium has the lowest electron affinity, minimum, and the maximum pulling power. Come on, I want to become stable. Electron, it's always in hunt. Where is electron? Where is electron? Do you have an electron? And that is nothing but fluorine. So fluorine has maximum electron affinity and cesium has the minimum electron affinity. So this is a concept which is contrast to ionization potential. And after this, 2 more properties left. Just go through this thoroughly. We'll start with electronegativity. You will say it is fluorine because fluorine, here I have done. Fluorine has the maximum pulling effect as compared to chlorine. So you will write it is fluorine and I will say wrong. Ha, yes, now this is the catch. This I was waiting for. Guys, your concept, what I have taught out here is perfect. There is no harm to it. Now look at the exception. It should have been fluorine, the maximum pulling power. Undoubtedly, I have taught the same thing out here. But the answer is chlorine. Now this is a twist. It's like a movie. Check this. This is an exception. Exception. Ideally, it should have been fluorine, but no, it is chlorine. Look at the story, what happens. So now we have this electron back. This electron is flying. It is pulled. The tendency of pulling is maximum by fluorine undoubtedly. I am not having any second thoughts over it. So this electron is actually just see, it's flowing. Chlorine is pulling it. Fluorine is pulling it. The victorious person has to be fluorine because the pull of fluorine is much more than chlorine. Lovely. So mother is calling, son, come please, I love you. The sun is coming. But the house is very small. The atomic radius is very small. And already there are 7 electrons sitting in the house. Come on, fluorine 2, 7. There are already 7 electrons present. So when this electron flows, the other electrons, the other children are nasty ones. They don't let this electron to enter. So there is no place because of electron repulsion and because of a small atomic radius. So this is a problem. The atomic radius of fluorine is small. Yes, mother calls the sun with pure love. The force of attraction is good enough, but there is also a force of repulsion because of the other electrons and because of the small size. Arey man, we don't have place in house and how can you join us? So then the electron goes to chlorine. So guys, the electron actually settles down out here because chlorine, the atomic radius is high and electron repulsion is low because of the size. There is more space in the family to accept one more child. There is more space. So my answer is not fluorine. This is an exception, please. It has to be chlorine. So the element having the highest electron affinity is chlorine, but the maximum tendency of pulling is fluorine. Fluorine almost won the race, almost, but the other nasty kids didn't allow it to reach the final destination, right? So this was a beautiful concept. So just go through this and we start with the next periodic property, which is electronegativity. The 4th periodic property is electronegativity. Electronegativity. Now, electronegativity is the tendency of pulling the electron, okay, by an atom, by the nucleus in the outermost shell. So it is nothing but the tendency, T-E-N-D-E-N-C-Y, I just forgot the spelling of tendency, yeah, sorry. It is the tendency to pull an electron, or in my language, can I say, it is the easiness. It is the easiness with which an electron enters into the outermost shell. It is the easiness with which an electron enters into the outermost shell, in the valence shell. Now it's very simple. If I talk about electronegativity and if I go across the period, again, sodium 281, chlorine, argon. Tell me one thing, if an electron again tries to enter, where will it prefer going? Of course, it will prefer going to chlorine, because chlorine can easily pull an electron and become more stable. So across the period, who has the more tendency to pull the sun, give more affection and love? It is the chlorine. So therefore, can I say the electronegativity across the period increases. Now some students ask me, sir, what is the difference between electronegativity and electron affinity? Look, electronegativity is the process, it is the property, it is the tendency, it is the inherent characteristic of a body, the virtue of pulling someone. Now say, for instance, for example, I look good. Yeah, I have the tendency to attract people. So I am quiet. I'm not speaking anything. I just look good. And just I observe that person. The person is attracted towards me. That is electronegativity, the tendency of pulling. But as soon as I open my mouth and I am hopeless at speech, I speak something like, hey, how are you? Oh, come on. That person is just going to turn and go somewhere else. That is like electron affinity. I know it is a stupid example, but I know you're going to remember such examples. I know my students very well. So if I, have the tendency to pull, that is electronegativity. But the person is approaching me. He's approaching. And when he speaks to me, I say, how are you? What are you doing? My voice is hopeless, right? My expressions are tremendously bad, derogatory. The person takes a U-turn and goes to the other person. And that is chlorine, just like electron affinity. So electron affinity is when an electron actually enters. And this is just a property of pulling, the property of attraction. Alright, so electronegativity across the period increases or decreases? Increases. The pulling effect is more. Down the group, if I talk about the electronegativity, right from hydrogen up till cesium. Again, the same explanation like electron affinity. Okay, down the group, can I say, as we go down, the atomic radius increases, nuclear charge increases, pulling effect obviously increases. Yes, but since the atomic size increases, the distance between the mother nucleus and the outermost shell is more. If the distance is more, radius is more, can I say that electron will not be much attracted, much pulled by the mother because of the high distance. So I can say down the group, the pulling effect, the pulling power decreases. So electronegativity down the group decreases and across the period increases. So if I happen to generalize the concept, it goes this way. Down the group and across the period, electronegativity across the period increases and electronegativity down the group decreases. Remember, right? Okay, after this, which is the most electronegative element? Most electronegative element is who has the most tendency of pulling? It is fluorine, undoubtedly. Look, the tendency of pulling is fluorine, but the electron will not enter into fluorine. It will take a U-turn and enter into chlorine. Because of that exception, you remember I spoke few minutes back. Because of the high electron-electron repulsion and because of a small atomic radius. But the tendency of pulling is fixed. The most attractive is fluorine. Okay, talking about the least electronegativity, it is cesium. Cesium. Fine. So this was about the fourth periodic property. Let's go ahead with the last periodic property, which is metallic and non-metallic nature. Okay, now it's very simple. As I said, as we go across the period, what is metallic character? What do you mean by metallic nature? Metallic nature is the tendency of losing an electron. The tendency of losing an electron. The easiness with which an electron goes out of the last shell. So I will say tendency, simple language, to lose an electron, and tendency to accept, to gain an electron. So this is called metallic character and this is called non-metallic character. Shortcuts, short forms are not allowed in the board exam. I'm just writing it for your convenience. We need to save time. It gets bugging. Okay, so can I say, tell me one thing. Sodium, I think it has the tendency to easily lose electrons. Very smooth. Come on, yeah, take my electron and go away. I want to be stable. So I can say the most metallic in this period, across the period, is sodium. And the most non-metallic, the one who gains the electron fast, it is chlorine. So can I say across the period, you need to write all those stuff. The nuclear charge increases, number of protons and electrons increases. Yes, shells remain the same. But I can say the tendency to lose electron decreases. So the metallic character across the period decreases and the non-metallic character across the period increases. Alright, if I talk about down the group, I think down the group from hydrogen to cesium, the one who loses electron very steadily, very readily is the cesium because of the less force of attraction between the nucleus and the outermost electron. And because of that, this electron can easily be lost. So I can say what is metallic nature? The tendency to lose electrons freely, easily is more metallic. It's said to be more metallic. So I can say cesium is the most metallic characteristic. Cesium has the most metallic nature. Okay, in case of elements, if I don't take francium into consideration. So I can say down the group, the metallic character increases and the non-metallic character decreases. Because if I take an example of fluorine, chlorine, bromine, tendency of pulling an electron decreases. Fluorine, we just did it, electronegativity. Fluorine has the most power to attract and pull the electron. Now that's a different story that the electron goes to chlorine. But the pulling power is of fluorine, na? So can I say the non-metallic character decreases? Fluorine maximum, chlorine less, and so on. So down the group, this is what happens. So if you ask me, sir, who is the most metallic in the periodic table? It is cesium. And who is the most non-metallic? And I will say it is fluorine. So guys, this was about the metallic and the non-metallic behavior. So now the final part of the chapter in which we're going to study about the neutron-proton ratio and just a table that how do these periodic properties behave across the period down the group with the maximum nature and the minimum nature, right? Go through this and we go with the last part of the chapter. Final part of the chapter, guys, the neutron-proton ratio, the NP ratio, that's what we call it as. Now it's simple. You take an example of sodium, yes, we call it as sodium 2311. 11 is the number of protons or electrons, and number of neutrons is obviously 23 minus 11. So 23 represents the mass. Mass, that means it is protons plus neutrons. Protons plus neutrons. Yep. Out of which protons are 11. So if you subtract, so 23 minus 11 is going to be 12. So the number of neutrons is 12. Alright, so we have protons, we have neutrons. If I talk about a ratio, the NP ratio, N is to P, I just substitute all of you all. 12 upon 11, approximately the answer is going to be 1.1. Isn't this answer close to 1? Close to 1. Of course. So I say if the neutron-proton ratio is approximately close to 1, we call the element as a light element. We call it as a light element by mass, by weight, right? So I will say that sodium is a light element because the neutron-proton ratio is tentatively, approximately very much close to the value 1. If you talk about another example of uranium, uranium-235, 92. That's the atomic number. So protons, the number of protons are 92 and the number of neutrons, you subtract them. You're going to get the number of neutrons. That will be 235 minus 92. That counts up to 3 minus 143, I guess. Yes, 143. Now if you take the ratio, the NP ratios, yeah, you just substitute 143 over 92. The answer will be approximately 1.5, close to that answer, close to that value. So I come to another conclusion that if the N is to P ratio is approx 1.5, that element, that metal is said to be a heavy metal. So guys, if I happen to differentiate between a light element and a heavy element, point number 1, the neutron-proton ratio, if it's close to 1, it's light. If it's approx 1.5, it's heavy. And we can definitely give one of the example in order to, just prove what we spoke right now. So this was the last part of my chapter, the last answer to my chapter. Now giving you like a beautiful table, a summary, a gist on the 5 periodic properties, who is the most and who is the least of each of the periodic property. Let's study about that in a tabular form. Right, guys. So talking about the first periodic property, the atomic radius. The second was the ionization potential. Third, electron affinity. The fourth one was, oh come on, I forgot, yeah, electronegativity. Yes, there you get it. And the fifth one was the metallic nature, metallic character, and the non-metallic character. Listen, the short forms are not allowed. Time and again I've told you all. So metallic character and the non-metallic character. Okay, I'm going to study about a gist. All right. Across the period, the variation. Down the group, the most of them and the least of them. Now that will help you exactly, right, to analyze the entire chapter in a tabular form. Okay, beautiful this is. So making a table. Yes. Fine. So talking about atomic radius. Come on. Can I say across the period from left to right, the size, the atomic radius keeps on decreasing. So atomic radius decreases. Down the group, the size of the atomic radius increases. The most the largest of all the atoms is actually francium. But I have told you all that francium is a radioactive element. So we can take an element above it, which is cesium. So the element having the most atomic radius is Cs. And the smallest size is helium. That's the first one for you all guys. Next, ionization potential. Across the period, can I say ionization potential is the amount of energy required to release an electron from the outermost shell of an atom? We've done this, come on. So can I say in ionization potential, which element across the period, can I say it's difficult to remove the electrons? So you need more energy. Ionization potential across the period increases, down the group decreases. The element having the most ionization potential, maximum, yep, it is helium. And the least ionization potential, least energy, is cesium. The third one, electron affinity. When an electron enters into the orbit, so electron affinity across the period, the affinity, the liking of electrons increase. A bond is formed easily. And down the group, electron affinity decreases. The most electron affinity element, okay, the element showing the most liking towards electron is actually fluorine. Yes, but we know there was an exception in this example. There was an exception in this answer. And the answer is not fluorine, it is chlorine. We have studied about this. I'm just having an asterisk out here to indicate this was an exception. The least electron affinity, cesium again. Fine. Electronegativity, again, across the period from left to right, electronegativity is the easiness, okay, of attracting the electrons. And definitely it increases from left to right. Down the group, electronegativity decreases. The most electronegative element is fluorine and the least of them is cesium again. And the last one. Metallic character across the period decreases and the non-metallic character across the period increases. Down the group, metallic character increases and the non-metallic nature decreases. The most metallic is cesium and the least metallic, can I say most non-metallic? So most metallic is cesium and the most non-metallic is fluorine, and this is vice versa. Right? So this was a gist, a summary chart for the periodic properties in a periodic table. So guys, this was the end of my chapter. What we have studied in this chapter was, first we spoke about the demerits, the defects, the limitations of the people who started with the locationing, the positioning of the elements in a periodic table. And then we were successful with the help of a periodic table given by Moseley. Then we studied about the significance, the properties, the 5 periodic properties, and we studied in depth about each of the periodic property. And at the end, right now, we saw neutron-proton ratio, along with a beautiful gist or a summary, which will just, it's eventually, if you do this much, you've actually completed the entire chapter, right? So just go through this, and if I happen to be erroneous at any point, just get it to my notice. Thank you.